Hey, hey guys, and welcome to the stream. I don't know if I'm live right now. Alright, uh, pretty sure that I am live right now. I'm guessing. Yup, I am live, and welcome to the stream. Just a second, I'll check on the stream and if it's working or not, and then I'll gonna get to what we are gonna do today. So yeah, just a second. All right, just a minute. I really wanna check if the stream is up and we don't have any issues with the connection and connectivity and stuff. Because the last time I tried streaming, I don't know why I wasn't able to really get I don't know what happened last stream, but I just wasn't able to do anything on the stream. So just a second, I'll check and see if everything is up and working correctly. Alright, is up and working correctly. Right, is up and working correctly. Okay, yeah, it is working. And perfect. So that means I think we can now start with the stream. Perfect. So, alright, so as you can see from the title of the stream, in this stream we are gonna try to create a neural network using plain numpy and python. So we are gonna be working out all of the mathematics required to build out the neural network. So this is gonna be a really cool video to learn how neural networks work, and I hope that you enjoy it. So let's just get started. So I'm gonna open up my terminal and we're gonna create the project. It should take a second. Alright. So I'm gonna cd to desktop and I'm just gonna make a directory named neural network from scratch. Alright. So I'm just gonna cd to this directory and I'm gonna create a main.py file and I'm just gonna open that up in Visual Studio Code. Perfect. So as I just told you, we'll be using plain numpy to make this neural network, but I'm gonna be using TensorFlow for just one thing, which is to actually load in the dataset, because we are gonna do this on the mnist digit dataset, and I don't exactly know where else I would find the mnist digit dataset, since I always just use the Keras datasets for that. And so yeah, I'm just gonna make use of that to load in the data. I'll just use TensorFlow, and then for the actual initialization and forward and backward passes, we'll actually perform the computations and derive the equations required. Alright, so let's just get started. So the first thing is we need to import uh, numpy as np and import matplotlib.pyplot as plt. Alright, and now we need TensorFlow, so from TensorFlow import Keras. I don't know why my laptop is lagging a bit right now. I hope that it goes away. I'm pretty sure you guys won't be able to see that in the recording, since it's upscaled to 720p by 60 frames. So yeah. So let's load in the data. So I'll just do a simple train images train labels test images and test labels is equals to keras dot datasets dot mnest, and we want to load it, so we just pass in the load data function, and this should load in the data for us and then split it into the training images, training labels, testing images, and testing labels. But currently, we have one major problem with our data, one that it isn't normalized, and the second major problem with our data right now, at least for me, is that the data that we are working with, the shapes of the data that we are working with, more specifically. What I mean is that currently the shape of the training images and the testing images is something like 60,000 by 28 by 28 for the training images and 10,000 by 28 by 28 for the testing images. And that's not exactly what we want, since what the problem is that since we are going to be creating a multi-layer perceptron, that's what we are going to be creating. So basically what's going to happen is that we're going to be dealing with three shapes. So when we actually, I'm sorry, three dimensions. So when we actually go about and perform the actual forward pass and the backward forward pass mode necessarily, we always do a matrix multiply with of the inputs and the weights. And right now, since we have a three-dimensional input and we're probably just gonna have a two-dimensional weight, that really won't work. So what we really need to do is we need to take our input and we need to compress it in a way that it is two dimensions and we also don't lose any actual information, you know. So the best way to really do that is to combine the width and the height dimension to just a single dimension. So we can take the train images and we can reshape it into a 60,000 by 784, since that's 28 squared. So first I'll just do a simple train images is equals to np dot reshape train images 60. Actually, the way I'll do it is just a train images dot shape 0 and 784. So this should work, and then we want to do the same thing with the test images. So test images, and we can just pass in test images. Alright, there we go. And that is all we need, I'm pretty sure. Alright, so now that we have done that, we need to go ahead and normalize our data between 0 and 1. And again, doing that is a very simple thing. So we can just do train images is equals to train images divided by 255.0 and test images is equals to test images divided by 255.0. I mean, I don't know if we're gonna be making like a really cool and like a really good neural network for this, since it's gonna be a very simple one. Because the thing is, we have to back propagate through a neural network also. And so if I do go ahead and create a pretty complex neural network, I'll have to go through several layers of back propagation, manual back propagation. Keep in mind, and it will just get too crazy. And frankly, I mean, it just will become almost stupid to actually do something like that. I mean, you know, it would be better if we just develop like a little library over it. And I don't wanna go into that right now, so I'm just gonna do like two layers. So I don't know if we are even gonna get an opportunity to actually test it on like testing data. You know, we maybe will just test it on like the training data, something like that. Alright, so now that we have reshaped it and normalized it, we can actually go ahead and what do you say, initialize the weights and the biases. So define initialize network params, and in here, do we need any parameters? I'm pretty sure we don't. Alright, so we can just do a simple weight1 is equal to 0.001 times np dot random, oops, random dot rand n. So we can generate a random array or random matrix, and now we just need to enter the shape of the matrix. Just a second, guys. Alright, so I had a sip of water, and if we go ahead and look at the documentation for np random rand n, you can see it, if you don't pass in anything, then it will just generate like a random double, as you can see. But then if you pass in uh, 2 and 4, then it should actually go ahead and generate like this matrix of 4 samples in each thing, and then 2 actual rows. So it's a row by column type of a matrix, and that's exactly what we want. So now we just need to determine the number of rows and the number of columns. So the best way to know that is if we just actually look up the rules for our matrix multiplication. So I actually prepared some stuff for that, and I worked through some examples myself off camera. And as you can see, once we reshape it, since we know the way matrix multiplication works, which is that you have a row by column, and if you have another matrix which is not of the same shape, then the other matrix should have the same number of rows as the number of columns in the previous matrix. So in this case we have a 784 over here, so that means weight 1 should have 784 here. And then the second parameter is like the number of neurons, which is a variable, and so when you perform the computation you should get this. And then we do the same thing with the second shape also, second weight also. So that's what we're gonna do. So in here we can therefore determine what we need. So we need a 784 and the number of neurons. So I'm gonna stay with like 150 for now. You can choose whatever you want for the neuron count. We ourselves will probably change it maybe in the future, but for now we'll just use this. I don't know what else will work. Alright, so another random, this is going to be the bias. So since we just need to add, this will just take in the neuron count. If you don't know why, that's because that's how matrix addition works. And if you don't understand, then I would recommend that you check it out. So now we need to initialize the second layer parameters. So np random random, and right now the output shape will be 60,000 by 150. You need to reshape it to something like 60,000 by 10, since we have 10 total classes, since our digits range from 0 to 9. So in this case, the weight 1 will be the weight 2 will be initialized to something like 150 comma 10, since we have 60,000 by 150 after this computation. And so after this computation it should be 150 in the rows, and then 10 for the columns. And then b2 we can just set as 0.001 times np random. A lot of people like to initialize especially the bias. A lot of people like to start it initializing the bias as just an array of zeros, and then they like to learn how you want to initialize the bias. Now that does work, I'm not saying that it doesn't, but in this case we're gonna first just try doing a random initialization of like not zeros and just some digits. But if that doesn't work out, then we'll go ahead and just do like a np dot zeros. A lot of people also just like to initialize all network parameters as 0, and then they like to learn it by themselves, because in a way that's cool, because a lot of the times your network parameters get initialized to something that is pretty bad, especially if you're going to be using like a deep learning library. A lot of the times the way your network parameters get initialized is by the type of initializers that you choose in your network for that specific layer. And so a lot of the times if you choose the incorrect initializer for that task, for that data really, what ends up happening really is that your initial loss will be very high, and then it will, and like the loss for the second epoch will be very very low, and that's not the best thing in the world. So you, what you really want is you want a pretty good initialization, and zero is kind of like a constant, and so it doesn't change between computer to computer and stuff, and so that's kind of why people like doing that, I'm pretty sure. But we're gonna just do a random initialization right now. So that we do a b2 and we get that, and then we can just return the parameters that we created: w1, b1, w2 and b2. Alright, so now we need to actually code out the forward pass. Now the forward pass is pretty easy to code out, since the equation used to compute the forward pass of a specific layer really is a very simple one. It is just equal to y equals mx plus b. It's just written in a different way. What the way we write it is something like z or a is equal to some sigma activation function. But you know what, let's not dive into non-linearities in right now. We'll dive into them in just a second. We're gonna have a dot between inputs times weights plus the bias. So that's basically just y equals mx plus b, and then we obviously apply a non-linearity to this, which is your activation function. So we can just code out the forward pass. So first off we need the a1, I'm sorry, the z1, and that just reminds me we need to take in the parameters for w1, b1, w2 and b2. So we can code out z1, which is just going to be a dot between the inputs. So we also need to take in x, the inputs, and the weights. So weight w1 plus the bias term. So we have a z1, and then for a1 we just need to apply our non-linearity. So in this case we need to code out the non-linearity. In this case we're going to use the ReLU activation function, so we have to code that out. So we can just do a define ReLU, and if you have ever looked at the ReLU activation function, it's basically that for all inputs that are 0 or lesser than 0 are going to be trimmed out to like 0, and for all inputs that are greater than 0, the inputs will be that specific number. So really we are just calculating the maximum. So we can just do a simple return np dot maximum of the x comma 0. So that's really all that we need to go about doing. Perfect. Alright, so for a1 we can just call ReLU on z1, and that should be good enough. But now we need to do the same thing for our second layer. So we can do a z2 is equal to np dot dot, and this time the inputs won't be x but it will be z1. So we can do a z1 with the w2 plus the b2, and for a2 it's again just gonna be another thing, but in this case we are gonna need another activation function, something that returns like a probability distribution, probabilities for each output, because this is gonna be our output layer. So like what we want to output from the model is a bunch of probabilities for the predicted thing, like the predicted digit in this case. So the best activation function for that is softmax, but I'm gonna use sigmoid for this right now. Because I really want to try out sigmoid. Main reason being, I don't want to code out softmax really right now. I mean, I've seen how it works. Coding it out for the forward pass is relatively easy, but coding it out for the backward pass is a pretty big pain, and I really don't want to go about doing that. So I'm gonna just code out sigmoid, and if it doesn't work, then we will go and code out softmax. So I know I know that softmax is the best choice for this task, but I just don't want to code it out. So we can just do sigmoid. If you don't know how sigmoid works, it's just 1 over 1 plus e to the negative x. And that's all we have coded up over here. And we're gonna have to do one more thing, which is just this. I'm just gonna do that. Since division is uh, like if you are more if you know according to the operator precedence, division gets executed first even in the computer, so that's why. All right, so for a2 we need to just apply sigmoid to z2, but this is still not gonna work. I mean, it's gonna work, but we still have one small problem, which is the fact that we have no loss function. So now we need to code out our loss function. All right. So for the loss function, the last time I was trying to work this out, I decided to use categorical cross entropy. The main reason being I really couldn't find out any like better loss function. I mean, sparse categorical cross entropy could also work, but I don't know. I just wanted to use categorical cross entropy. So this is exactly how categorical cross entropy looks like. It works stuff. So yeah, we are just gonna use this. Perfect. Now coding this out is gonna be a little complicated, but it's okay. I mean, so we can just do a categorical cross entropy, and for this one we'll need two inputs, which is the one not encoded true and the prediction. So in this case we can just say now usually the way this is that the prediction is denoted by the term y hat, and the truth t is denoted by the term y. So we could do that, but in terms of actual parameter passing, it's not really a kind of a good thing, since we could just pass in truth and prediction and it will be a bit more readable. So truth and prediction. Alright, so then over here we can just do a simple actually first, before we even do that, we are gonna face one problem with this, which is the fact that we look at truth, we see that it is a one hot encoded truth, and that's actually that's okay. But if you look at the prediction isn't gonna be one hot encoded. However, there are gonna be certain times when the prediction that you have, I mean for the probabilities that you get, there's going to be a chance that one of those probabilities is 0, and that's not what you want, since you're doing a log of it, and so log of 0 isn't going to give you like it's just kind of undefined. I mean so and so this won't work, so this part of the equation will break, and so when you actually multiply it with t1, your entire loss function will just break. And I mean, if your loss function breaks, then when we actually perform the optimization step and the back propagation step, it just won't work, because you won't have any loss in the first place to actually compute all those derivatives for the backward pass. So we need to actually go ahead and make it so that pi never gets to 0. And the best way I think I have seen people do that is just do a np.clip. So we can just do an np clip, and basically this should clip the values between a min and a max. So we can do prediction, and usually we set some very small value like some epsilon, which is going to be like a 1 e to the negative 5. You can set whatever value you want over here. Really, it's like the smaller the better. I mean, you could say something like 15, but I mean, I'm not gonna do that, since I mean at one point if you add a certain number of zeros, it really doesn't make any sense. So here the minimum value is gonna be epsilon, and the maximum value is just gonna be 1 minus epsilon. Now I don't exactly know why we do a 1 minus epsilon over here, but I'm pretty sure it's actually because of the fact that you want to keep the mean of your stuff constant. So basically, if you add an epsilon term, if you have like some graph, if you imagine that your thing is like a smooth little graph or smooth little curve, and the mean of it is just going to be the middlemost value. Now, if you want to keep it constant, you're going to face one issue, which is the fact that if you have this little epsilon term which is clipped, then your mean will shift slightly. And if you don't want that, then we can also clip the data from the other end so that the mean never shifts. And that's really why we do this. Or at least that's my best interpretation. Maybe there's some other reason. I don't know. So we have the prediction which is clipped now. We don't really care for the truth. So now we can do a simple multiplication and then do this. Now, the way I have seen the code for this at loss function is something a bit different. I'll show you what I mean. So, the way I actually learned a lot of this is through a book. You go to the, so I have this book called NNFS, Neural Networks from Scratch in Python, and that's really from where I learned a lot about these activation functions and the code required to build them out. And I kind of wanted to show you something. Now I'm gonna download this book since that book has my email address on it, and I don't want you guys to see that. So if we just do a simple neural network from scratch, search, there it is. This is what we want. Just click on here and do that. Right. So I wanted to show you guys something which is uh, kind of what I need to work on for the loss function. Basically, it is the fact that the way we define the loss function is the negative log likelihood, and uh, currently, if we just follow the equation that we were seeing previously, we would actually not get the correct output. I actually did try it out once or twice, and I didn't get the output that I wanted. So we're gonna have to look at the code for this. You know what? I'm just gonna see if I can get the code. And I don't know why my Chrome isn't responding right now. It's kind of a bad thing. Okay, why aren't you responding? Just I'm okay if this gets shut off. You're kidding me? Why isn't my Chrome responding? I mean, my VS Code works. Whoa, what's happening? Okay. Okay, why do we have this lag over here? Please, I hope that I don't have any lags in the stream. Just a second, I'm gonna have to check if I have any lags. Oh, come on, please don't. Because if I have a lag, I mean, this 28 minutes of stream just went down the drain. Just a second. I mean, I don't see any lag. Whoa, what's happening? Alright, so I don't see any lag right now. And if you don't understand, then I would recommend that you check it out. Alright, so okay, cool. So there is no lag. Perfect. Okay, so I'm just gonna go ahead and show you from that book what it is that I'm talking about. I just hope that this doesn't lag again. Alright, so, oh come on. And it's not because there's any virus or anything. Okay, I just hope it works this time because I really can't open that copy up. So yeah, hopefully it works. Alright, perfect. So now it's actually loading. I don't know, the last time we opened it, it just wasn't working. Uh, Wait a minute, if I can just get the kit up for that, maybe I can just show it to you quicker. There we go. Is this? I don't think I want this one. I think I want to get the book code. Yeah, this is the one. Okay, so this is the repo that we want to look at. The book code. Alright, perfect. So this is the book code that we want, and I don't exactly know which chapter did this entire backprop thing uh, take place in. So I'm just gonna open up like the final chapter so that we get everything, and then we'll just kind of take out the cross entropy code from that. Okay, so where is our thing? Input value softmax linear optimizer Adam. Yeah, so this is the loss function. Okay, cool. So this is what we want. So if we look at the categorical cross entropies forward pass, you see that we are clipping it. This is correct. But okay, so if we look at it over here, what we have done is we have done the log of the correct confidences, which is correct. And then we are just returning the negative log likelihood of that. And correct confidences, if you look at it, is just an np dot sum between the two. So wait a minute, that's yeah. So basically what that means is you're doing a log of the final value. I don't know why we were being shown to take the log of just that, of just the predictions. I don't know why that's the case. But whenever I go up to Google, that's all they say. I don't know what that is. Maybe I'm just interpreting it wrong, something like that. So I'm just gonna do this as confidence is equals to a simple truth times the prediction, and we just want to do a np dot sum on that, and that's all we really need to do. Maybe we'll need to do something else. I don't know. Do we need anything else over here? I'm pretty sure I don't. Alright, and basically, the reason why we are not doing a dot product here is because we don't want to do a dot product like a matrix multiply. We're just trying to do element wise multiplication. Since the shape of truth and prediction is going to be exactly the same. And then we can just do a negative log likelihood is a negative np dot log the confidence, and then we can return the negative log likelihood. Perfect. That is all we need for the categorical cross entropy loss. And so now we can just do simple loss is equals to categorical cross entropy applied on the A2. So A2 will be output of logits or probabilities, and then we produce the loss from those probabilities. So then we can just do simple return of Z1, A1, Z2, A2, and loss. Perfect. So that's all we need to do for the forward pass. As you can see, I mean, we haven't written a lot of code, we have barely written any code, but the stuff that we are doing is pretty complex. Alright, so Now we need to code out the backward pass, the big thing. So the backward pass is unarguably the most difficult part of the coding out a neural network from scratch. It's relatively simple in terms of actual math. I mean, it's really just basic calculus. So if you understand derivatives and like the basic rules for derivatives and like partial derivatives, then you should be good enough, more than good enough to understand backprop. Really, it's pretty simple. It's just that it's kind of difficult to get the intuition. Over here, I'm expecting you have the intuition because I'm not gonna dive into that right now. I mean, I have an entire video on backprop. If you wanna check it out, go ahead and check it out. I would recommend that you do, since I'm expecting that you know that stuff. Since this is a stream, I won't be explaining all of it. So yeah, so I'm just gonna do a define backward, and this should take in a lot of parameters. Now I'm gonna work this stuff out pen and paper. Now I've already worked it out, but I kind of want you guys to really see how I would go about doing this if I didn't have all of this like already worked out. As you can see, I have already worked out all of this stuff, but I'm gonna set that aside for just this stream. I'm gonna close this, and the best way I really like to work out backprop. Okay, speak a little louder. Sure. I think I did start speaking a little louder since like 5 7 minutes ago. So yeah, hopefully that's audible now. Alright, so the best way I really like to go about doing backpropagation is I usually just use this book by named Mathematics with Machine Learning. Basically, because this book goes into how you could go about doing like ordered automatic differentiation and stuff, which is pretty cool. So if you go over here, as you can see, it has a chapter on backpropagation and automatic differentiation. And this chapter is really cool since it goes into why stuff works. And as you can see, we have your inputs, your feed forward one, then you have your two and stuff, and then you have your loss, as you can see. And then as you can see, they have gone ahead and actually coded out, like, I'm sorry, not coded out, worked out the mathematics for that, which is pretty neat. Okay, why did I go to the last page? Just a second, I'm gonna have to go back to this. Alright, so now what we need to do is we just need to construct an equation like this, that then we can use automatic differentiation and certain backpropagation tricks. Really, to be honest, automatic differentiation is just a fancy word. I know, you might look at it as like, some crazy trick or something, but it's actually just chain rule. It's really just chain rule. It's just that you're applying chain rule in this type of a context, which you probably might have not seen if you're just like a math student, or you haven't worked in computer science and neural nets before, and so you might not kind of understand the way we go about constructing the equation, since it's a lot different. So if you have checked out my backprop video, you'll see that we always create a computational graph, since that's the best way for anyone to approach a backpropagation step in case you aren't using any library. Since the problem is, if you don't construct any graph, you will probably make some kind of mistake in the backprop step. Now the cool thing about backpropagation is that in this case we aren't going to be having some crazy complex exponentials and stuff over here. Like, we won't have any powers. We just have a very simple equation, so we don't need to deal with roots, we don't need to deal with cosines. We need exponential, but the only reason why we need to deal with an exponential is because of the fact that it is in our sigmoid function. So if we separately differentiate the value on the sigmoid function and the categorical cross-entropy loss function, we really won't even have any non-linearities and stuff to deal with. We just need to differentiate a y equals mx plus b with respect to x and b. So that's why it's so easy, I would say, to work with this. And I know it For some people, this might still sound a little complex, but you'll see in a second that it's not too crazy. And to be honest, you know what? I won't work this out right now because you guys won't be able to see that, and I want you guys to see how I actually work this out. Open this up. All right. Cool. So, as you can see, I've just gone ahead and coded out a part of our neural network over here. Not coded out, written out. So we have a here. Now, obviously, if we wrote out the full thing, we'll also have like a loss term over here. So the first derivative that you would find out in case you had a loss term, which we have, is going to be the dl by dA. Now dl by dA really is just going to be the derivative of the loss function. Since when you use the term loss, what that really means is the term loss, the term categorical constant entropy isn't an output term, it is an operator, just like ReLU. We are operating on the inputs. So what we are going to have is we're going to have another straight line, we're going to have a circle that is categorical entropy, and that will output the loss. So when you do a DL, which is the D loss by DA, what you really are doing is you are just finding out the derivative of the categorical entropy loss function in this case. And that's really all that backpropagation is. I mean, you're just working like inverse chain. So that's really why it's super kind of easy. Alright, so that gives you the dl by dA. Then you have to have a dl by dz. So dl by dz is just your dl by dA, whatever output you get from that. You can denote it by anything, d loss, whatever. And that times dA by dz. Because if you look at it, this is really just chain rule, right? Because you have a final function that's being acted on by several functions, but then those functions are also being acted on by several functions. So it's kind of like f of g of h of x, something like that. So that's really why we use chain rule in this case. I mean, that's the intuition. That's the way I understood that the reason of using chain rule. I mean, whatever works for you. But yeah, we do need to use chain rule for that. So we then get this. So we get that. Now in this case, I just wrote a d-value and not the loss function, since I didn't consider a loss function over here. If you would obviously add that loss term over here. So it doesn't mean that my answer is incorrect. It's just that I haven't included the loss function in the computational graph. That's why. And then for the B one, we just do this. Again, it's just chain rule. I just said that. And I have actually denoted an intermediate of inputs times weights as Q. And so when we do this, when we do a d by dB1 with respect to Q plus B, the Q goes off to 0 and the B goes off to 1. So we just get that dA by dB1 and dA by dQ1 is just one thing. It is just d-ReLU with respect to Z1. Now keep this in mind, because this means that if you have a plus sign, if you have a plus operator between two operands, which gives you some output, some result, the sum, then if you compute the gradients dz1 by dq1 and db1, they will be the same. So the gradients for dz1 will flow equally to dq1 by db1. And so if you have this, you can just quickly obtain this. And when you're going to be differentiating the weights, we are gonna need the derivative of q, not b. So you would have to now work out the derivative for q, since you know that dq is equal to db. So you can then differentiate the weights with respect to the pies also, which you wouldn't be able to. So technically you can't, but just because q and b have equal gradients, you can. So then you can go ahead and do that. I mean, I'm pretty sure I've gone out. There we go. As you can see, I've gone ahead and done that. You can check it out. It's pretty simple. And yeah, I hope you understood how this works. Alright. I mean, I spent quite some time on this. Okay, how long has our stream been? 44 minutes. Alright. So, I mean, here's what we are gonna do. What I think I'm gonna do is I'm gonna go and do back prop in the next video, next stream, most probably. Mainly because of the fact that I mean we have already spent 45 minutes on this, and uh, I usually have not. I usually don't do like too long streams. I mean, I think I've done a couple of hour and a half long streams, but yeah, I'm just not. I get kind of tired. So yeah, I'm gonna stop streaming right now, and in the next video we're gonna code out the derivatives for ReLU, sigmoid, categorical cross entropy. I'm also gonna work them out in front of you so you can understand exactly how it works. And then we are gonna code out the backward pass. Once we figure out these derivatives, which believe me they aren't too complex. I mean, this is just simple quotient rule. This is just simple log, like the derivative of log. And ReLU is just a very simple thing. Since it's discontinuous, you just do a simple, you differentiate the two parts separately. And yeah, it's just super simple stuff, and we'll get into that later on. So that's it for this stream. I hope you enjoyed it. And in terms of like videos and streams and stuff, I mean, I think you're gonna get a lot of content in the following few days, just a few days, cause, and then you're gonna then I'm probably not gonna be uploading for like 2 3 weeks. But yeah, you can expect a lot of content to be pumped out in the coming